Um, Good morning, everyone. Welcome in a moment. Yeah, great. All right, we're live on YouTube. Good morning, everyone. My name is Maria Fonja. Welcome to week 3 of AI Saturdays Lagos second research cohort. So today, it's all about the paper presentations. And we're very excited for our 8 presenters who I'm going to introduce in a moment. But I also want to let you know the rest of the schedule of this cohort. Next week, we will be having another round of workshop talk and round table panel discussion as we've done in the past 2 weeks. And the last week would also have another paper presentation, but in that week it will be focused on re-implementation and the presenter discussing what they have done so far regarding their chosen paper. Okay, so the goal of today is that our presenters are able to share with us the high-level overview of the approach that was used in the paper that they're presenting. Of course, we want them to also be able to convey us the problem in the research paper, what they're trying to address. So we'll be having 10 minutes presentation with opportunity to ask question for 2 minutes. And you can ask your question live or depending on the time we have, we may not be able to take all questions. So we also invite you to use Slido to put down your questions. And today's presentations are structured into 2 sessions. In the first session, we would have a set of 4 presenters. Then we'll come to a break of 2 minutes. Then we will come back after the break for the last set of presentations. As I mentioned earlier, we have 8 presenters, and I want to take a moment to introduce them all right now. So we have Adeshola Josiah, who's a robotics and IoT intern at Unilag Design Studio and final year systems engineering student. And we also have Zainab, who's an aspiring research engineer that is focused on mathematical reasoning in AI and its applications. Olumide is a tech enthusiast that is passionate about AI, robotics, and empowering global Nigerians through innovation. Kausar is an aspiring AI enthusiast. She's eager to explore how AI shapes a safer, smarter world. We have Isaac, who's a research associate at Upanzi Network. He specializes in robotics, AI, and their applications in healthcare. Olushola is a student at Lagos State University College of Medicine. And Zion is an experienced data analyst with 3+ years in deriving actionable insights from structured and unstructured data. Finally, we have Uthman, who is an industry researcher with data, API, and cloud expertise that is seeking growth after a career break. So without further ado, I will kickstart the first session, which would include Zion, Olushola, Isaac, and Bakari's talk. But first, I would like to invite Zion to give a talk on exposed diffusion, learning to expose. That was a mistake. Learning to expose from low light image enhancement. So Zion, the floor is yours. Please go ahead to share your screen.
Thank you so much, Tajumadin. Good morning, everyone, and wherever you're joining from. I'm excited to be presenting this morning. Please kindly confirm if you can see my screen.
Yes, I can see your screen. Thank you.
All right. Thank you so much. So, like you introduced, I'm Zion, and I'm a data analyst with Emerging Africa Group. And this morning I'll be presenting the paper Exposure Diffusion, Learning to Expose for Low Light Image Enhancements. And these are the authors that wrote this paper. And before I go further, I think from this paper, the keyword there is exposure diffusion. And what exposure diffusion is more like an image processing technique that uses physics-based exposure model and to restore images. So, and physics-based model, what the physics-based model does is to, restore images from noisy image instead of pure noise. And so the what they intend to do is just to expose image to better lighting conditions using the physics-based exposure model. So in my presentation, we've spoken about the title. So I'll be giving us a brief overview of the problem, why the problem is important, the background work that has been done, the goal or the hypothesis, the method that was used in tackling this problem, and what's the results they got after the experiment was done. So what problem do they intend to solve? So um, images captured in low lighted conditions usually have poor visibility, high noise, and low detail. And also the methods that were used previously, they give undesirable results, especially for images that has like an area with maybe more exposure. So, by the time they expose the image, there is a part that is overexposed, and it's a big problem because you eventually get an undesirable result that you're unable to use. And another problem is the previous models are usually um they are usually um like they use a lot of resources, and you are unable to compute with you know, you need extra model capacity to actually run the model. So they need a better model that is natural and efficient enhancement. So that is the problem that this paper intends to solve. And why is this problem important? Why is it important for us to why is the problem important? The problem is important because low light images are usually difficult to interpret, and in industries where well exposed images are essential, they are unable to use those images. So industries like security, photography, and medical imaging. So in these fields where well exposed images are essential, some methods like this are very, very important. Also, the limitations of the current method. So the existing methods actually require complex processing or result in unrealistic output. So like we said earlier, there's a need for a model that can handle these limitations, and so that it can be valuable for real world applications. So that is why this problem is actually very important to solve. So looking at the background work. So for traditional low light enhancement, it relies on deterministic neural networks, which often produce unrealistic results. So what this does, what the previous enhancement method does, is just that the neural network directly maps the low light image to brighter images, but it struggles to retain the details and minimize the noise in the image. So it produces unrealistic results. Also, for the traditional diffusion models, previously, yes, it's powerful for restoration tasks, but it has high computational cost, and it eventually um, gives us less realistic intermediate output. And the reason is because the traditional diffusion models, it starts training the models from pure noise. So it goes through pure noise before it now do a reverse diffusion to get the image. So most times there's always a gap between the image and the real image that is supposed to be generated. Also for raw image processing, yes, there have been works where their like raw images are being used as the noisy image instead of just pure noise, and it gives better noise modeling, smaller domain gap between synthetic and real data. So what is the goal of this paper? The goal of this paper is to develop a model that enhances low light images by simulating real exposure processes for natural and efficient image restoration. So we want to develop a model that enhances low light images, and at the same time we are mindful of the computational efficiency, and also we want to a model that that will give us an efficient image. So what are the hypotheses? The hypothesis is one, a model that incorporates um, exposure physics can produce natural brightness control on enhanced images. So we expect that when we use this model, even for areas where there's a bit of brightness. So for instance, in a low light image that has an area where there's a high lightning. So by the time this model is being run on it, it gives us an enhanced, it doesn't overexpose that area. Also, the second hypothesis is that incrementally adjusting exposure can yield realistic images without complex denoising processes. So it reduces the noise or improve the efficiency. So that is what this paper intends to achieve. So what is the method used? The method used, like I mentioned, is the physics-based exposure model framework. And what that method does is it mimics the real-world exposure to simulate natural brightness and contrast changes, and helping the model to handle noise patterns typically found in low light settings. So it studies the patterns in the noisy image, and it integrates both the physics-based exposure model and also the diffusion-based model that was in the system before. Then also there's an adaptive residual layer, and I believe that the reason why this was proposed is to adopt different noising strategies for areas with different noise to signal ratio to screen out the side effects in iterative refinement. So because naturally when you use um, traditional diffusion um, the traditional diffusion model, after the iteration has been done, so there's always overexposure. So this paper is proposing an adaptive residual layer where different noising strategies are being used, so that the side effects of iterative refinements, when the intermediate results have been already well exposed. So we do away with having to overexpose an area where there's already enough exposure. So lastly, for the method, the progressive enhancement process. So a model uses the actual low light image and progressively refines it. So it progressively refines it. It doesn't just map it at once, which is um the traditional method. That one just maps the dark images to bright images, and it gives an unrealistic result. But for this one, it does it progressively. So after the experiment was done, it was evaluated, and using two major, two widely used raw image low light enhancement datasets, which is the ELD dataset, that's the extreme low light image denoising dataset, and the SID, that's the see in the dark dataset, was used. And from the results, we can see that the first graph here shows the PSNR, which is the peak signal to noise ratio, versus the SSIM, which is the structural similarity index. So the peak signal to noise ratio is just a measure of the image quality, with higher values indicating better quality. So if we have a high PSNR, it means that the image quality is actually better. And the SSIM is measures the image similarity. So how the higher the value, it means that it's closely similar to the reference image. And from the graph here, we can see that after testing it with different amplifying ratios, we see that stable image enhancement quality, there's stable image enhancement quality across the various low light intensity, and it outperforms the base model, which requires more parameters and computational resources. Also for the, sorry, I'm trying to, okay. So also for the other graph, which shows the comparison of models in the number of parameters, flops, and inference time. So what this shows is that the exposure diffusion achieves better efficiency with fewer parameters and low flops. So flops is floating points operators per second, which represents the operational efficiency. And the point size here, this point size actually represents the inference time with large points indicating slower processing. So if we have a large point, you can see that the baseline is actually, it has more processing time than the model that was, the model that was trained by the authors. So we can see that after comparing with, the parameters and comparing the floating points, the inference time, we can see that there's better efficiency with fewer parameters and low floating points compared to the baseline, which is attributed to the use of the physics-based model, which minimizes unnecessary noise removal steps. So because it's not starting from pure noise where it has to, train the noise before it gets to an image, then now denoise it back. So this one just starts directly from noisy image. So those unnecessary steps have already been removed, and it focuses on the computational power on actual enhancement tasks. So I that is the results. So looking at it, like we've mentioned earlier, looking at the performance of this model or this method, you can see that yes, it outperforms the traditional methods by maintaining more detail while reducing the noise, and also it gives there's efficiency, there's faster inference time since it starts with the real image instead of the pure noise, and also there is generalization. It works well across different exposure levels and noise conditions, making it adaptable to various environments and devices. So I would conclude now by saying that after testing, the testing on the benchmark data set shows that the exposure diffusion improves the image quality, it performs well across different lighting conditions, and achieves efficiency with fewer parameters and faster processing. However, other data sets, so we can, other data sets can be explored, like medical imaging or extreme light conditions can be used to enhance the generalizability. So you can just try other data sets to ensure that, the models can be well generalized and can be used across different domains. Thank you so much. I hope I was able to manage my time well. Thank
Well,
you.
thank you so much, Zion. Thanks a lot for your presentation. We approached 12 minutes on your presentation, so we will not have a lot of time at all to take questions. But I want to give you an opportunity to at least answer one question, which is on Slido right now. So the question says, Zion, does the model need low light pictures that have been correctly brightened for training?
No, no. It needs the dark pictures, the dark images. That's what we use for training. And that's why the data set that was used here is the extreme low light image. That's the ELD, extreme low light image data
Okay,
set, and the same with dark data sets, yes.
okay. So thanks a lot, Zion. If
Thank you
you
so
can,
much.
please stop sharing. Then please, everyone, give Zion a virtual round of applause. And keep coming with your questions. You can put it on Slido, even if we cannot answer it now on the call. We can always come back to all questions, and maybe Zion can take some of them offline as well. Okay, so our next presenter for today is going to be Olushola Aremu. Olushola, please share your screen as soon as you can. It will talk about ADDNet, an effective deep learning model for early detection of Alzheimer's disease in MRI scans. You have 10 minutes for your presentation. Please try to fit everything in 10 minutes so I don't have to interrupt you to say something makes me feel bad. So,
Yeah, thank you. Thank you very much. Please kindly confirm you can see my screen.
yes, your time starts now.
Okay, so my name is Aremolu Shola. I'm a final year medical student, and I'll be presenting ADNet, an effective deep learning model for early detection of Alzheimer's disease in MRI scan. And the authors are of the papers are Farid MM, Zikra S, Ahmed G, Mahmoud S, Aslam M, Giuliani SF, Mustafa A, and Assad M. So, so this is going to be my outline, overview of the problem, why this problem is important, the background, hypothesis, objectives, methodology, results, and discussion, the limitations, and conclusion. So, the um, yeah, so the paper proposes a deep learning model called ADDNet or ADNet, which is an acronym of Alzheimer Disease Detection Network for classifying Alzheimer disease using MRI images. So the authors intended to address the issue of detecting Alzheimer disease, um, especially the early stage Alzheimer disease, by addressing the problem of class imbalance in the data set available using small stomach algorithm. And the proposed model performed better than previous models. So while Alzheimer's disease, it is a progressive neurodegenerative condition, and it causes memory loss, cognitive decline, and eventually functional impairment. And the problem with Alzheimer's disease is the cause is unknown, and the earlier the diagnosis, better the prognosis for the patient. So early diagnosis and treatment allows Alzheimer's disease patients to maintain the highest level of cognitive and functional ability possible. So there is also no cure, just management. So yes, so the background of the paper, like I said, it is a neurological brain disorder and it causes dementia. Dementia is just memory loss. And like I said before, it's early and accurate diagnosis of Alzheimer's disease is crucial for therapeutic treatments. Deep learning models have been applied or have been used to um, automate medical imaging diagnosis, including Alzheimer's disease, and some of them have achieved a very significant results. Also, convolutional networks have shown promising results in detecting Alzheimer's disease. However, the medical data sets are usually imbalanced because in, in practice, the number of people with the disease are actually smaller than the healthy population. Also, within the number of people with the disease, the classification of different severity of the disease also differs, and you find out that most people come in when the condition is severe. So we have limited data for early stage Alzheimer's disease. So this imbalance poses a challenge for training accurate deep learning models. So the paper introduces a new architecture that is specifically for detecting the early stages using MRI scans. So during the early stage of Alzheimer's disease, there is a stage called preclinical where there is no clinical manifestation. The person is fine, but there are changes in the brain already that if you catch that early enough, you can help the patient live better. So the hypothesis proposed in this paper is designing a model from scratch for Alzheimer detection would outperform existing pre-trained models in terms of all of these metrics, and addressing data imbalance using smooth to make would also improve the performance of the data. So, so now to the methodology. Data set was gotten from Cargo, and the table on my left shows the description of the data. You can see that the data is imbalanced. We have some classification of available data as low as 64 and have high at 3,200. So after applying oversampling, able to increase data to 3,200 for each one of them. So methodology also involved pre-processing. The images resized were resized and rescaled, and one autoencoder was used to take care of the categorical um, variable of the class. Then after which the imbalanced data was addressed using smooth to make, and data was split into train, test, and validation. And the ADDNet model was used to train the data and get our results. So these are the evaluation metrics. So the ADDNet architecture consists of four convolution blocks, which uses value as the rectifier activation and 2D average pooling, then two dropout layers for regularization, then they were flattened out before they were passed into the dense layer. The dense layer of the architecture two, and eventually the the classification was done by soft max layer. So this shows the architecture of the model properly. So you can see that there are four blocks of convolution, and for each one of them, the kernel size was 5, and the initializer for the kernel was a glorious uniform V2. There are others which can be used, and a ReLU activation was done, and then the result was pulled, and that was done over and over for block 1, block 2, block 3, block 4, and also the number of filters as you see changes. Then a dropout layer, two dropout layers were used to minimize overfitting, drop out just blocks of some nodes in the neural network. And because a fully connected layer would only receive data in one dimension, so the output from the convolution needs to be flattened, and as you can see here. And also for the fully connected network, the kernel initializer was also brought uniform 2, and a value attribution was used. So based on this architecture, the ADDNet model was evaluated and compared to other state-of-the-art models using metrics like accuracy, F1, sensitivity, core, and so on. And it was noted that the hard nets optimized with smooth stomach achieved peak performance. And yeah, and this is shown in this table when the proposed model ADDNet was compared to other previous models. And you could see that for most of the metrics, the ADDNet performed better. Also, using small stomach oversampling technique significantly improve the performance of the model. This would put more insights or give more insights into that. And you can see this was without small stomach. The receiver operating characteristics for the models ADDNet in my lower right here, and compared to others. But when the smooth stomach sampling was used, you could see that the area under the cuff increased significantly, and the model outperformed every other model. So, what are the limitations for this particular study? I noted that data set was from Cargo and it was small, and this can really affect the ability of the model to generalize, and which because you are using this for hoping for a clinical application, so it would affect the application of the model in real world data. So future research can be done to validate the model's performance using a larger and more diverse data set. So in conclusion, the study introduces a novel and effective deep learning approach for early detection of Alzheimer's disease. The model, when combined with small stomach oversampling technique, shows a significant improvement in accuracy of diagnosis, so leading to earlier intervention, early diagnosis and early intervention for anybody with Alzheimer's disease. Thank you.
Oh, thank you so much, Olushola. Well done with time management. We have two questions for you. One of the question is that is there anything specific to Alzheimer's disease in the network architecture, or could the same also be used for other diseases?
Okay, thank you very much. Um, there is nothing specific for the Alzheimer's disease. I believe that it can also the same architecture would also be able to detect or can also be used to in other diseases. However, performance for that disease may be
Okay.
reduced or increased.
Okay. So the other question we have here, if you can quickly take it, is can you explain the small to tech sampling balancing method? Just maybe some clarification about how they're balancing. Yeah.
Okay, smart to tech is first an oversampling method. So usually when you have imbalanced data, there are majorly two ways to balance. Either you oversample as you increase the 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 class with the lower amount of data, or you reduce the other class. So smart Tomek uses a oversampling algorithm, which is um, synthetic minority oversampling technique, and it basically increases the class that is lower, and also the other part of it is the Tomek, which kind of clean the data. It removes form of noise. It removes noise from the data because while you are trying to increase the sample, there might be some data points that may be quite similar or in the same space, but in different classes. So you want to remove those parts of the data. So that's what Tomex does.
Okay. Well, thanks a lot. Let's take the rest of the questions offline. Please give Olushola another round of applause. Next, I would like to invite Isaac Fanny, who's going to give a presentation on Omni H2O, universal and dexterous human to humanoid whole body teleoperation and learning.
Hello. Thank you
Hi,
so much.
Isaac. Yeah, we can see your
Ah,
screen, please. Thank you.
okay. So I'm going to present the work on Omni H2O, the universal and dexterous human-to-human whole body teleoperation and learning. This is a work on control for humanoid robotics and teleoperation, basically by Tyran He and colleagues from Carnegie Mellon University and a Chinese university. Sorry, I couldn't get the name fully. So what is the main problem here? Humanoid robots are increasingly popular. We see them in our spaces. We see demo videos from Tesla. Uh, we see the impressive things they are doing. Sometimes we keep doubting, are they really staged, or these are really things that these robots can actually do at the moment. The interesting thing is that there's a good number of them that are staged. So dexterous manipulation for these robots are still not as fluid as we would expect and as is shown in some of these videos. So this work is to enable a better control of these robots. These robots have a high degree of freedom. It makes it difficult to control them in real world settings for full body tasks. And you might ask, why actually humanoid robots? People keep asking, why do we want to make robots that look like us? I think some of the reasons are that robots that look like us can easily navigate our environment. We design these environments for ourselves. These robots will be able to navigate these environments, and also they would allow us to study cognition and then be able to improve performance, make these robots more useful to us if they look like us, and we also look at some of the things that guide our own cognitive capabilities. So existing systems, they struggle to manage complex real-world manipulation and movement because there's a question of stability and dexterity and control. So these robots, they have a potential to actually improve, like be used in many fields, like in healthcare, in manufacturing. If you have an assistive robot that actually looks like human and can actually navigate around like human beings, it makes it much more useful to us. And robots can also collaborate with us better. So I've mentioned the issue with stability and precise movement coordination. The key questions that the authors have tried to address is actually to check this framework and see if robots can actually accurately track motion in simulation and in real world. And also does the Omni H2O support versatile control interfaces, and also if we can collect data that we can use to learn and train other agents in teleoperated demonstrations. So the main hypothesis is that a universal control interface that combines teleoperation and autonomous learning can improve humanoids robots' ability to perform full body tasks with stability and dexterity. And they aim to develop a versatile control system that enables collaboration through virtual reality, through voice commands, and then RGB cameras. We have a pipeline that looks like this. There is a VR-based collaboration to generate the data set of 6 everyday tasks. And then we have a policy training that utilizes a teacher-student learning framework. And they are trying to implement a reward-shaping universal kinematic pose interface for stable dexterous control. This is what the whole method looks like. We have human motion retargeting. We have simulation to real life training. And then we have a universal real-world teleoperation and learning. This data set is the first of its kind, and it's available now actually to be used for further work, training, improvement. The results that were obtained outperformed the previous system in simulation and also in real-world motion tracking. There's a higher success rate and then lower mean per joint position error. There's greater stability under disturbances. The current limitations we have is that there's still some noise in the robot odometry, and then this causes deviation in the motion goals during teleoperation. Also, there's a lack of safety guarantee for like extreme disturbances, and there is currently still limited autonomy. So the system struggles with complex real-world tasks like navigating staircases and maybe some tight corners. And the system stability is also challenged in dynamic or unstructured environments. What are real-world scenarios where we can actually use a setup like this? We can use it in a setup where we are trying to do some teleoperation tasks, where we want to be able to control this humanoid robot with a natural language, and where they are like in a situation where we have disturbances, and also where we want this robot to be able to learn to autonomously complete tasks. What's the future work that is being envisioned? The future work is to enhance the ability of the system to traverse, to do some complex upper body motion, and then also to incorporate advanced sensors and develop better learning algorithms so that these robots will be more effective, and also there will be a reduced error rate and improved success rate. So currently, the Omni H2O design supports this dexterous whole body manipulation, as we can see in some of the videos obtained on the project site. And this allows seamless integration of teleoperation and autonomous control. And I hope to implement and recreate some of these results within the limit of the computational capacity I have currently. So thank you so much. I would appreciate any questions.
Thank you so much, Isaac, for your presentation and for your very nice time management. So we have a few questions on Slido. One of the questions says, in your opinion, should robots move like humans or figure out their own movement that might be more efficient? E.g., human cannot do some movement.
Yes, I appreciate that question. Actually, it's a question I've seen colleagues work on, currently reproducing biological motion. So it depends on the type of robot and the purpose of the robot. If you are using like, let's say, robots on the assembly lines where you need precise movements, there's little obstruction from the environment. And I mean, everything is just like it can be preset. You know that no obstructions will come from this way. You can design a different control system for them. So in that setup, they don't need to move like humans because our movements will not be the most optimal for that. But if you are working with assistive robots, social robots in the classroom or for therapy or in some setup where there's actually a merit for them to look like human humans, then it's very, very important to replicate this biological motion because first of all, it would make the interaction smoother. That's the first thing. The second one, it would be much more safer. You can't imagine like a big, let's say, cooker manipulator moving at very high speeds that can be dangerous to you around you as an assistive robot. But when you have systems that move like humans or that replicate biological motion, the safety is much more guaranteed for people in that environment. And I think the last one is reducing uncanny valley. So there's the issue of uncanny valley where people feel a bit creeped out or creepy, like when they see robots around them that are doing some strange things. So when you see a robot that actually moves much more smoothly, it reduces that issue, and then it opens a whole new world of possibilities of what we can actually use these robots to do. So again, in short, it just depends on the robot and what you want to use it for.
Thanks a lot for that answer. One more question that we can take here is, what are the 6 everyday tasks that they looked at in that work you presented?
So the 6 everyday tasks looked at, I think I didn't have it on the slide for some reason. You have like, just a second. I am trying to get it out. So you have catch and release. So the humanoid robot catches and releases objects, focusing on dexterous hand movements. You have squat. So the robot is able to do some squats. You have rock, paper, scissors, interactive tasks requiring dexterous hand movement and coordination. You have hammer catch. That's humanoid robot catching a moving hammer, showcasing a fast reaction time. You have boxing. Then you have basket pick and place. So picking up and placing a basket, that's to demonstrate the ability to handle objects with precision and coordination.
Okay, that's good. I was told by our time tracker that it seems you're really good in time, so we have 1 more minute for you. So if you don't mind, there's also another question that asks that. So is it safe to say that the paper is about data collection? So given all of these different tasks, they collected the data for it, or how would you re-explain it to someone that is still a little bit confused about the goal of the paper?
Okay. I think the paper built up on the first human to robot framework that was developed earlier by this same group. And I think this is a demonstration of actually this framework being implemented, and then at the same time also introducing this data set that can be used by many other people. So right now, I don't have the Unitary robot in my lab here or around me, but with the data that they've collected, I can actually do some work myself here.
Fantastic. So everyone, please help me give Isaac another round of applause. Thank you so much for being here. Our last presentation for the first session is going to be given by Bakari Kausar. She'll be talking about automated spinal MRI labeling from reports using large language model. Kausar, the floor is yours. Thank you.
Good morning, everyone. Please, can you hear me?
Yes, you're audible.
Okay, great. Good morning, everyone. My name is Kausara, and I'll be presenting the research paper, Automated Spinal MRI Labeling from Reports Using Large Language Models. So this is the outline for this research paper. Can people hear me, please? Hello?
Yes, you're audible.
Okay,
Please
I'm so sorry.
continue.
It's just very quiet. So
No
brief
worries.
overview.
I can also talk to you if you would like, but you're audible.
Sorry, no problem. So a brief overview of the problem was that they figured that labeling reports could be time intensive, and then aside from being like very like time intensive, it will also like be expensive because it will require like professionals to be able to like correctly like report the like to label the report rather. Then so the authors came up with a way of automating extraction of reports, mainly on radiology reports, and then they also went further with their testing to train an image model to be able to classify these conditions. Why the problem is important, like I said before, automating reports can be stressful and time intensive. So automating labels can help in that type in time efficiency. Then it also give room to create like larger data sets that can be used in different studies. So background of this study is that large language models have been more accessible and can be used for like different conditions. And even though there's an emergence of GPT-4, it is still very expensive and costly. So the goal of this research is to create an approach for extracting labels for vision models, which can be used for vision models. The methodology used, so there are two sides to this report. The first phase is extracting structured labels from radiology reports. It involves the user imputing conditions with a brief definition about the condition and what the condition entails. Then it is fed into an LLM model, that's a language model. And then the results of the LLM gives like a summary of the report of the condition. And then the structured labels are the yes or no. So it also gives a structured label about the condition. So a yes or no condition, whether the condition is present. Then the second phase of this methodology is where the labels are fed into a classification model, an image classification model, and then the classification model sees the condition and tells whether it is there or not. Then here it's seen that the labels were fed into ResNet 18 encoder, which is a type of image classifier encoder, then gives an embedding result. Then the embedded result is fed into SEM, which is also another algorithm for classification to predict the condition, right? So the results and discussion of this paper was that they were tested, so 3 language models were tested against each other following the summary and query method, right? So the direct query involves just query models, then the summary query involves using the language model as a summary model and both as a query model. And it was seen after several testing that the Llama 3 summary query method performed better than other methods. Then for the MRI classification, the author decided to use the ResNet and the SEM technique, and it was seen to perform best in condition of stenosis. So yeah, the limitations of this paper will be that they are currently like forcing the model to only give a yes or no answer, right? And then there are other like methodologies that the author didn't include, so he didn't really give like a full concept of the paper. And then there are some medical reports that could not be used because they exceeded like certain windows or like certain word tokens that the LLM models could accept. So the the author proposed the conclusion of this paper that the author was able to like propose a extracting model for extracting reports, radiological reports. And then it was seen to be cost effective and also time effective. Then extracted models were trained to achieve classification. Then these are the references, and thank you.
Thank you so much, Kausar, for your presentation. Also very good with timing. So we have a couple of questions on Slido. One of the questions says, to clarify, is the LLM asked to generate the labels, which are then used to train the classifier?
Yeah.
Okay.
Yes, it is. Yes. Sorry.
The other question we have here is, how was performance measured? What are the metrics used?
So the metrics used were the area under the curve and then the EER. Sorry, I'm to check for that. And the EER was used to generate the EER labels were used to give results on F1 score and balance accuracy. So the EER is, yeah, those are the metrics used. I don't know if I'm clear.
Okay, so it seems we still have more time to take questions. So do we have any questions from the audience right now? It seems not the case. So that's okay. I will come back. I will come to share my screen again. Please, can you all give Kausar another round of applause? So maybe we'll just go into an early break and then we'll come back for the next session. So, but before we do that, I'd like to thank all of our session one speakers, Zion, Olushola, Isaac, and Kausar. Thank you so much. This was like you all presented interesting topics. And we still have time to interact, to ask questions. Maybe some of these topics are interesting to every attendees. You can connect with the speakers. All of our speakers have done a very good job to identify things in the paper that may be improved, and then we'll still come back in week 5 with our presenters to share with us what they did, how they re-implemented it, what were the challenges, were they even able to reproduce the results in the paper, and hopefully that helps you to get more feeling or more understanding about the papers that are being presented today. So now we will go into a 2 minute break where you can stretch your legs, but we also like you to please fill the attendance form. Use this moment to fill the attendance form, which has been shared on the chat right now. So we'll take 2 minutes. Then when we come back, we would have a presentation starting with Adeshola Josiah. We go into a break now. Thank you. Okay, welcome back, everyone. Did you have a nice stretch? Okay, I was told that we only have 2 responses so far on the attendance form. So please do so as you know, as fast as you can. It really helps us, and it also helps us to be able to give you the certificates because it's a criteria we are using this cohort. Okay, so next I would like to introduce the second session for today, and it's the last session. We have 4 speakers, Adeshola and Zainab, Uthman and Olumide. And I'm not so sure if is Uthman on the call? I was going to check while we're on the break. Uthman, are you on the call? I see you. Yeah, you're on the call. Nice. Okay, so yeah, anyway, so now next I would like to invite Josiah to share his presentation and walk us through the paper.
Thank you. I believe you can hear me.
Yes.
Okay. All right. Okay, I'm sharing. Good morning, everyone. So I'll be presenting on reinforcement learning with A-star and deep heuristic. So this paper was prepared by Kelsman et al. And the other people that worked with him. So the keywords are Aleph star, which is a new algorithm, reinforcement learning, DQN, A-star, and path planning and autonomous systems. All right, so this paper actually focused on creating like an hybrid algorithm, combining A-star and deep heuristic, or what we call learnable heuristic. So, and the reason why they did this was basically for path planning. And as you know, path planning is essential in robotics and autonomous vehicles. So these are like one of the core algorithms that guide the navigation of any autonomous vehicle, like we know about Tesla and maybe other vehicles that are self-driving cars, basically. So the traditional algorithms that has been used has been A-star. So what A-star does, that A-star is like an informed path planning algorithm or an informed search algorithm. So what it does is that it tries to um, choose the best path to follow based on 2 key things, and those key things are which represent the cost function. So one thing is, so you can look at my screen. So for instance, if this is the starting point and this is my end goal, so from year to year, from this, let's say from A to B is like my real cost function, while the heuristic is like the estimate from this current node, as it's usually called, like if you want to use specific terms, to this goal. So you are combining heuristic, that's just like a guesswork or an estimate cost, with the real cost. And heuristic and A-star is very efficient for path planning. That's if the heuristic is well defined, or if the heuristic is good. But using reinforcement learning like DQN, DQN stands for deep Q network. So what DQN does is that DQN make use of neural network, particularly in most situations, convolutional neural networks, that's CNN, for adaptive decision making. So what this means is that we're talking about environment that are visually complex. For instance, different one of the core challenges aside all of this for self-driving cars are usually like, what is the car seeing and what kind of environment does the car find itself based on the image input. So for cases whereby we don't have fixed heuristics like I talked about, and this paper tried to solve the problem of fixed heuristic. Like the regular heuristic we have is always like estimating with a straight line, or using the formula of what is it called, like Manhattan distance or Euclidean distance, to like estimate the remaining part of the goal. But in this case, Aleph Star tried to use combined learnable heuristic. That means trying to estimate the Q value. Q values are like reward system. In reinforcement learning, for every action that the state, for every action that maybe the stuff go through, there's always like a reward, which is like a Q value. So the value is just like, you can assume it as a certain number. So instead of having a fixed number in this case, we are using deep neural network, that's CNN, to estimate the value using convolutional neural network. So for instance, now in cases whereby there is obstacle on the road, or we have traffic situations, so Aleph star algorithm tries to do better. But we still talk about the difference between it and DQN. So Monte Carlo research has also been existing and is useful for game theory, like the AlphaGo that was popularly used by, I think, Google DeepMind, if I'm not mistaken. So, but it's computationally intensive, and it's kind of uses random search. It's not really effective. It's not heuristic. So the core research, what this is trying to solve, is trying to combine A star. The limitation of A star is that it relies on a fixed heuristic, so it's not flexible to situations that the maybe dynamic environment for the autonomous vehicle. So why MCT, that's Monte Carlo's tree search I talked about, they're only efficient for in games theory because they do the job well, but they are computationally intensive. DQN is also very good, but the issue with DQN is that DQN is not really futuristic. DQN is just about a single step. So it only makes decision to just estimate the Q value. Q value is like the reward function. So let me explain this properly. So for instance, let's say this is a car, like this is a car right here, and the car wants to change the lane. So changing the lane by taking one step, you can use DQN to estimate. Maybe there are several rewards. Let's see, if I go here, my reward is, let's say, 20. If I go in, my reward might be, let's say, 2. If I go in, my reward might be, let's say, 5. So what the agent is going to do is that the agent is going to choose the best reward. So that's the base of reinforcement is about. Agent, reward, and actions, most standard states. So it chooses this part. But the issue with DQN, that's deep Q network, is that, for instance, let's say I move to this other place, and it does not cater for the end goal in mind. So even if my car moves here, but at the end of the day, there's a car in front of me, or there are like several cars in front of me, and at the end of the day, I still get late to where I'm going to, or an accident occur because I chose poorly, because I'm just about the immediate value. So one of the core things that A star is solving. Sorry, I'm moving. One of the core things A star is solving is that it's combining Aleph star, that's the name of the algorithm that they made. It combines A star path planning algorithm and learnable heuristic, like I've talked about. So it creates like an adaptable path planning. And what it does is that it creates like a search network. So it creates a whole defined path. It creates a defined path from the start to the finish. And it can also actually do back propagation and like improve on the rewards and from what it has learned. Okay. So I think I've talked about this. Talking about it uses CNNs to predict the Q values, and it's quite efficient. So what this paper actually does is that it actually solves the limitation of A star. A star is like, according to them, is one of the best algorithms if you are making use of a very good heuristic, but just because of dynamic environment. So that's what they are doing this. And another thing about Aleph star that I've not mentioned is that it uses soft maximum updates. So it's trying to improve between exploration and exploitation. So exploration for search algorithms in AI is about us trying to find all the paths that lead to a goal. Exploitation is like choosing the best known paths. So soft maximum try to like balance it. But I think DQN, if I'm not mistaken, uses add maximum. Okay, so in this paper, they use the simulated driving environment. They use pixel based simulation. They use that to predict like Q values we see in it. And the reward function is like one of the key things, because obviously it's reinforcement learning. So what the experimental step they took was that the nodes were expanded by predicting Q values. So Aleph star is kind of futuristic. It builds the whole tree for you based on the best Q values that are selected. then it does back propagation, as I've said, so it can update the Q values, and also the press is iterative, and also another thing that is not as computationally intensive as DQN, So just summary. So Aleph Star outperforms an n-step DQN. And another thing is that they could not test it with Monte Carlo search. That's the only limitation that I saw in the paper. Right. So that's it for that. Thank you for listening. So I can take your questions.
Thank you so much for your presentation, Josiah. And we are open to questions now. If you have any question, please put it already on Slido. Thanks for people who have put questions. The question we have here right now is, common problem in Arrow is that policy gets stuck in a suboptimal policy. Does Alexa, I think this is how it goes, up with this? Josiah, you're muted in case you're talking.
Okay, yeah, thank you. So okay, so based on policy, so Aleph Star will actually solve this issue, because the reason is that is building from A star. So the reason why A star algorithm is maybe one of the best for informed search algorithm is that it has a fixed heuristic. So the heuristic actually guides it to get to a goal, unlike others like Monte Carlo search that is uninformed. But the barrier that we're having here is that the heuristic here is usually fixed. So in this case, the Aleph Star will actually shorten the path, and we actually that is the word, get the job done. So I don't know if that answers the question.
Oh, okay. If it does not, please, whoever asked it, feel free to ask follow-up questions later. And there's another question that says, what is hard maximum? How does that work? You mentioned soft maximum, hard maximum. I guess the person that asked the question was just curious about how you define hard maximum.
Okay, so for hard maximum, so as I said, soft maximum like balances. Okay, let me just move to one part. So I just want to use one image. Okay, I want to use the same image as an instance. So for hard maximum, like let's say this car wants to change its lane and it moves here, and do because of the reward here is the highest reward. And let's say this reward, it moves to this place, but at the end of the day, found out that it is in a bad spot. Like it's in a very bad spot. Maybe there's another car obstructing it, but it's going to run into a crash at the end of the day. So hard maximum will just maintain that exact lane. So because of that is like the next best reward. But for Aleph Star, because it uses soft maximum, it's not just about having the best reward function. It's about checking that, okay, even as I've gotten this reward function, what would be like the cumulative reward? What is going to happen at the end of the day after I've taken a decision? So it checks future things that is going to happen after taking a decision. So that's like the difference between both of them.
Thank you so much. Please give Josiah another round of applause. And next, we will have Zainab, who will give a presentation on solving Olympiad geometry without human demonstrations. Zainab, please share your screen. Hello, Zainab. Can you hear me? Okay, maybe Zainab has some technical challenges. It seems like that. Okay, so while we wait for Zainab to hopefully rejoin. Zainab, can you hear us? Okay, we'll just move on to our next presenter maybe. So our next presenter is Uthman, who's supposed to give a talk on modeling tabular data using conditional GAN, but unfortunately, Uthman just messaged that he's not been feeling well, so would not be able to give the presentation. And I happen to know that particular paper, and I happen to have given a presentation in the past, maybe 2021 or something, when I started my master's. So I could, I mean, if you are interested, I could, share something about that. I'm very familiar with that particular paper. But that's only if there is time.
Hello?
And you're interested, I could do that. Zainab, we can hear Zainab now. Okay, now Zainab is back, so we just stick to our current schedule. I will let Zainab go next, and Olumide will go afterwards. Then, if there is still time and you're interested, I could give the presentation for Uthman. You have to pardon me. I didn't prepare for this, but I can wing it maybe. We'll see. Yeah, Zainab, please go ahead.
Okay. Can you see my screen? Sorry.
Yes, we can see your screen.
Okay. And you can hear me clearly. Sorry.
You're perfect.
Okay. Okay. Hi, everyone. My name is Zainab Musumola, and I'll be presenting solving Olympiad geometry without human demonstrations. So I was watching the author's presentation on this, and they spoke about how the proof of Fermat's theorem was what inspired the whole paper, and Fermat's theorem was recently solved, and it took hundreds of years to solve. So the question is, can we build like a computer system that, if a problem like this springs up, it does not take like hundreds of years to it doesn't take hundreds of years to solve, can solve them in feasible time frame rather. So decided to focus on geometry problems from Math Olympiad as like a toy version of this grand challenge. Then the problem statement. So there's scarcity of human translated training data for geometry, and even if we have this data, how do we now how do we translate this into something that the computers can understand? And also the existing methods, they rely heavily on symbolic engines are logic machines. They use formal methods, so you just have like a machine that has like you know machines that have like set of instructions. It follows the instructions, so anything other than what it has as instructions, it cannot do beyond that. So no creativity or whatever. So there are also, when you're solving geometry problems, to prove something, say for example like AB equals to BC or something like that, you have to add like constructions in between to prove one AB is equals to BC. But as the problem gets more complex, it might get tricky. Adding constructions, like making constructions rather, might get very tricky. So it can be quite hard to solve. So why theorem provers? This is a test of logical reasoning and problem solving. So if we're able to, if we're successful at this, we're able to put forward a substantial benchmark for testing and demonstrating the progress of AI in logical reasoning and understanding, which is like a step towards like everybody talking about super intelligence and what have you. So what did they do? They introduced alpha geometry, a neurosymbolic system. A neurosymbolic system is a combination of neural networks and symbolic engines. So neural networks, from our normal language models, and symbolic systems are the ones that I spoke about the other time, that use formal methods list of with a list of what do you call it, instructions to solve a problem. So they fuse neural networks and symbolic systems, and they use it to prove not just geometry, Euclidean geometry to be precise. And this they solve this problem without involving humans. So what they mean by that is that they don't see examples of the computer does not see examples of what humans have done to solve these particular problems. The computer itself generates synthetic data to solve this problem and like train itself. So also when it solves a problem, the problem that you see is something that you and I can read and understand. So the approach is, as I said before, neural network and symbolic deduction engine. The language model is trained to generate insights and make these auxiliary constructions I spoke about also. And the symbolic deduction engine is called DDAR as a technical name in the paper. So this is what makes the mechanical deductions and tries to solve the constructions. So here you can see like a simple problem. Let ABC be any triangle. AB equals to AC, and they are asking you to prove if ABC is equals to BCA. So how this is normal elementary school math, geometry math, and if they ask you to prove this, you most likely put like you know a line in the middle and say, okay, AB equals to AC, BD is equals to DC, and with the set of rules with set of rules you have I forgot to say, sorry, I made the mistake, I'm sorry. uh, okay okay, sorry, I did not make a mistake. So ABC, so with this now, with putting this line in the middle, you are able to see that ABC is equals to BCA. So how does alpha geometry solve this? It uses the symbolic engine to solve it, because the symbolic engine has like set of instructions, as you said before, to that that helps you solve this type of problems. But if the symbolic engine is not able to solve this problem, it now sends it to the language model, and the language model can now like make suggestions that why don't you put this line here, why don't you put this line here, and if you put this line here, then sends it to the symbolic engine. If the symbolic engine is not able to solve it, it sends it back to the language model. The language model makes so there's like a continuous loop actually till the symbolic um engine is able to solve that problem. You will see E here, that is IMO 2015 P3, as is more complex than this problem here, and it was able to prove this, but it was able to prove this after 109. It took 109 steps to prove it. So symbolic engine, that is one part of the alpha geometry, sorry. So the symbolic engine is grounded in formal logic, as I said before, and it follows these rules to systematically work towards conclusions and solve problems. And it has two parts. It has the geometric deduction and the algebraic reasoning. So the geometric deduction is like set of rules, like I mentioned here. If you see here, you see something about collinearity. These are types of geometry rules that we use in solving geometry problems. And the algebra, it's just you know add algebra to make they come together, solve the problem or prove the theorem. Then it uses these geometric rules and algebraic reasonings. There are different ways that it can do that rather, and the paper spoke about Gaussian elimination. So so the model uses symbolic engines to synthesize millions of theorems and proofs, and it uses the symbolic engine to generate this data. And this data that was generated was about 100 million synthetic theorems with proofs, and it involves more than 200 proof steps. If you I don't know if you can see this this image clearly, but you'd see like a random premise, let's say like a problem, something that you want to solve. You see here, and you'd see the symbolic deduction you try to like make, different. These are nodes, so it operates like by applying. Sorry, so this one here is like this random premise, which is like the first input, and it now processes data, then it constructs like what the paper called a cyclic graph, which is this in the middle, and it is like a structured representation of like how the conclusions that the engine is trying to come up with to solve this problem. So you see here, when it made this, it came up here, but it was wrong. So you'd see it is blurry. Then here also, you got here is not, it wasn't the correct answer, but this one now is correct. So what it now does is that then it now does it's then it goes back to do like a trace back, where it takes like the smallest set of facts like needs to prove that this is correct. So the smallest, the how will I put it? The connected nodes that are like important to get to this solution, it does a trace back, and this is what it now uses to like train as synthetic data to like train the model and what have you. So you have the premise, which is the starting point, which is here, and in the middle you have the logical steps to get to the end, which is the solution. Then what did they get? This was benchmarked against like 30 IMO problems, that's the Olympiad problems, and they were able to solve 25 out of this. And prior to this, they were using Wool's method, and they were just able to solve 10. And you'd see here that the alpha geometry and the gold medalists, they're almost on par. And they made sure that when they solved these problems, they verified with human experts from the competitions and stuff, to just to confirm quality, that they are doing the right thing. So here is like a more detailed this table is a more detailed stuff for the bar charts. So here you see that whose method is about which is the previous state of the art, solved 10 out of 30. Here you'd see the normal deduction engine here was able to solve 9. Then the deduction engine plus the symbolic engine, their symbolic engine, which they used the deductive reasoning and the algebraic reasoning, they were able to solve 14. And if you see here, the alpha geometry was able to solve 25. That is adding the symbolic engine plus the neural network. They were able to solve 25 of the 30 questions. So that's about that with the results. But from my own observation, actually, the neurosymbolic neurosymbolic method is actually very good, and I think it's like state of the art and stuff like that. But then again, the intuition is not really intuiting at the end of the day. So here you'd see the original problem. I don't know if you can see it well, but you see the original problem here. This one was solved by a human. It's something that you can like write out in a page of paper, and you'd see that they try to like intuitively break down this problem into simpler ways so you can solve the problem. But here, the the alpha geometry paper the alpha geometry system actually took 110 steps to solve this problem. 110 steps. So as much as is intuitive, from my own observation, I think that it's also like, I don't know, if there are more complex problems, it will take too much time, more steps, and all those kind of things. So as someone said it uses brute force. So, and again, it doesn't conform to aesthetics that we humans are concerned about, simplicity and stuff. It just constructs anything that doesn't work goes into its learning process and what have you. So, broader implications of this, they demonstrated that the utility of synthetic data in complex problem solving, which is like very important for maths reasoning in AI, by the way. There are not a lot of maths data and stuff like that. So the use of synthetic data without any human demonstration is like one of the big things that is connected to this paper, and and in the future we should be able to apply this to other mathematical domains with similar challenges. Thank you.
Thank you so much for that presentation, Zainab. And we don't have time, but I'll let you take one question. And the question is that LLM do hallucinate. Can errors be introduced into the proof like that, or would the symbolic engine prevent that?
Okay, so first off, I would like to say that the model that was used was trained from scratch with core examples of this. Yeah, all LLMs still hallucinate and what have you, but by the way, that's where symbolic engine comes into, because if the model suggests something, if it does not work, the symbolic engine will try to, it doesn't know if it works or not. I mean, so the symbolic engine tries to, like, prove that or work on it. If it doesn't work, it sends it back to the language model that, do another construction or suggest another thing for me to work on till they find a solution.
Thank you so much. Please, another round of applause for Zainab. Next, I'd like to invite Olumide Buhari to give a presentation on incentive-aware federated learning with training time model rewards.
All right, thank you very much.
Zainab, can you please stop sharing so Olumide can share? Okay. Olumide, let me quickly stop sharing for Zainab. Olumide, please go ahead.
Okay, all right, good morning. Thank you very much. Thank you, everyone. Thank you for joining all over the world. And good morning from Nigeria. Okay, can you see my screen now?
Not yet.
So sorry about that. Okay. Oh. Okay, all right. Can you see my screen now?
No, it does not show that you're sharing anything yet. Did you click on the share and
Yes.
okay. So when you click on share, you see a bunch of desktop, and then you can click on the one you want to share, and you have to click another button
Okay, all right,
that
okay.
says share.
All right.
Perfect.
Very good.
Now we can see it, and
All right,
you
thank you.
just need to put it in presenter mode, and we're good.
Okay, all right. Yeah, thank you very much, everyone. Okay, so the topic this morning is incentive-aware federated learning with training using time model rewards. Okay, now let me quickly dive into it. All right, so what are time model rewards? They are just forecasting models, synthesized model for data generation and forecasting problem solution. Okay, all right. So this morning, we'll explore more on these predictions using our time model series. Okay, what's the statement of the problem? Now, the problem is with everyone and at everyone's stand. Okay, so my research is based on the health sector in Nigeria, especially the hospital, both urban hospital and the rural hospital and the large clinic hospital as well. For example, okay, all right, so we'll be generating a healthcare system that is fragmented into one data sources that can help patients discover their health symptoms. For example, okay, so let me just read it. Okay, you have a malaria and we are using one hospital just because of relocation from one state to the other. The hospital could not provide your health data all because of the limited access to healthcare system in Nigeria. So this time series model will forecast into you having your own health data, which can also be shared into another hospital where you are domiciled or where you can go. So, okay, so the smaller hospital that you have around you, the primary healthcare system, have your data. Some of them are not well equipped in this AI world presently. I think they only sometimes use the discretion of either symptoms that you give to them before they can give you solution to your healthcare problem. All right, so let me quickly dive into it right now. Okay, so you have a malaria and you're probably what's it called? Your health center is somewhere at Surulere in Nigeria, and probably you have another hospital that you went to maybe on the island and the same health issues, but different doctors, different medications, different symptoms. Now, this model will be the one that will be predicting the centered, what's it called? Health issues, challenges that we're giving to you. Now, in our public health needs, we have faced a lot of challenges, e.g., the Lassa fever, the cholera, and so on. Okay, all right. The Nigeria's data protection NDPR does not allow sharing data for personal reasons into healthcare systems, and we don't probably have a good health data in our health sector in Nigeria. This model will be the one that will be creating a health sector. It's an AI and an app that will also be given to everybody or allocated just like your NIN to have your data, symptoms, health challenges. So if you have a malaria in the last 6 months, okay, now what symptoms are you seeing now? What could be the challenges? How old are you? You have your age, you have your description. Okay, so if there is, for example, okay, 20 people stay in Surulere right now, and 18 people have come to the hospital to complain of particular symptoms. We can predict, this model can help us predict the actual cause and the actual symptoms or a particular problem that are associated with these symptoms that people have come to report at this hospital. So to divulge what's it called, a model, an algorithm to build and say, okay, all right, these particular people, 18 people out of 20 people have come to report their cases. So they know a particular problem and challenges that are associated with this. All right, thank you. So, okay, moving on, the impact on the health system, there'll be a leverage for the federated center, which can improve disease prediction, diagnosis, and so on, and which will also be reallocating resources into both human and urban population. Okay, all right, so our data model is our centralized model whereby our doctors, our nurses, and our healthcare workers will be given the same data that a patient has to modify their health status and their health, Okay, all right, let me quickly take you down to health, okay, all right, so this data predicts that, okay, using our local model and the federated learning model procedures, you can also receive that when we propose a local model, the scheme for this federated learning will help us achieve a global incentivization objective, given the convergence of these results. Now, for example, okay, all right, my data shows that I have a particular place on the island that presently, there is an outbreak of cholera due to their, environmental pollution, climate change, and all that. Okay, all right. So this AI model will be predicting such cases if there is need. What are the urgent actions to do? What are the urgent models to be presented for them in a theoretical manner to guarantee a framework and explore a model that will reward everyone, even if it's higher performance or the what's it called. Now, under this visualization, you will see that the Earth model in the what's it called, federated learning, the iterations, the percentage of health status of people living in the rural area and the urban area, the rural health status is more than the people living on the urban area. Okay, now, okay, I did a, what's it called? Sorry, okay. Still on this, my data. Okay, also, it will also be needed for you to be aware that this our model will be predicting our health sectors to give a fine-tune of giving our patients a good medication and a good guideline on their health perceptions. Right now, okay, moving ahead, what's our goals? Our goals and the hypothesis is just to design our incentive-aware system that will motivate hospitals within the large and small scale to contribute to the national model using the same federated learning model and the time series. Now, our hypothesis, by introducing real-time rewards, we'll be basing our quality on each hospital's contribution, which can bridge resources in urban and rural areas that will lead to equitable participation in overall healthcare in Nigeria. So my model that I'm introducing this morning is the model that will cater for the needs of not just the rural area, not just the urban area, but for a whole general country presently. So, okay, all right. Now, for another example is we lack data in our hospitals, being that some people are not even well encouraged to go to the primary healthcare center, be that as may be, that as close as they are. They prefer sometimes to go to the pharmacy to get a prescribed medication, and which is more or like the health challenges, and is not good and is not encouraged. Normally, you're meant to have a data, or you're meant to have a data and an app that tell you your status. So if you are feeling any symptoms, you should be able to tender that apps and see the symptoms of the last, maybe in the last 5 months, the last 6 months, what's your health challenges? What have you gone through? So it can help us to predict the symptoms you are having presently, what you do, so that we can give a well-equitable resources and we can prescribe a good medication, or if there's any other thing that we can prescribe. So this AI model will be the one that will not help us, that will not lack in our health sector, but it will give us a go ahead and give us a bridge healthcare. So, all right, the methodology. The methodology will be to train our models locally on patients that never leave their premises. So you are talking about children who, in this weather right now, there's a particular disease that is, what's it called? So if 10 out of let's say, okay, 10 out of 20 children were brought to the clinic or to the hospital, and we can diagnose them that, okay, this is a particular that they have, the same thing applies to an adult who have also come to the hospital. All right, so the quality of this data will be using a metrics like disease prediction, accuracy, and data rarity, which is very rare in the rural area. It's also helps us to stimulate our urban hospital and test the effectiveness of our incentive structures. All right, so this data that is maintained will be maintained only through the federated learning and the Nigerian data privacy protection, because you are not expected to share anybody else's data except the person himself. And no matter what, no third-party sharing of data. The only data is only applicable to you and very usage to you. So moving forward. So the results will help us in our participation rate in our rural clinics to participate actively in getting the data, collecting data. It also helps us our model accuracy for improvements, whereby by the time we are predicting, it's also not just prediction, but it will benefit our data sources from a rare disease that might arise in this case. Another thing is also give us a reward. Though the challenges will be there, which is the challenges of data inconsistencies between the urban and the rural hospital in variations and record keeping. All right, this book and this paper will suggest today that there's a need for us to build an algorithm and a model that will help us in the time series to have a more quantitative, what's it called? All right, my conclusion is this federated learning model in the healthcare will help us and ensure equitable participation from both large and small hospitals, the urban area and the rural area. Some locations in this country right now, Nigeria presently, are still lacking this healthcare system. And whereby they are lacking system is just because we haven't built a modem and a data that can help us reach to them. So there should be an app or a model on AI that can help us predict their urban health challenges, either being the adults or the children. All right. So the future reference is needed for us to optimize. This is like a forecast, like I told you, like federated learning using our model. So it will help us to address participants, infrastructures, and limitations. Thank you very much.
Thank you so much, Olumide, for your presentation. So we have some questions for you. One of which is, why does the doctor on slide 3 have 3 hands?
Okay, all right. 3 hands. Okay, all right. So there's another patient that is taking track record of the number of another nurse as a lab scientist nurse that is taking record of other data of patients coming to the clinic. And just like something I mentioned, I said data disparities. So the data disparities in these cases, a patient is coming from a background who haven't been to the hospital, who haven't had a health issue in the last 6 months, came to the hospital, and it was being asked, okay, what are the symptoms? All you could just say is, I have a malaria. And it's okay, all right, what are the symptoms of malaria? All because you are just aware that, okay, you are feeling sick, you are nauseating, you are having headache, slight headache or heavy headache. So it will help us, yes, it will help us to predict from here to know the number of, at a particular period of time, to help us predict the number of diseases that might arise in a community.
Yeah, thanks for that. I don't know if I'm correct, but I think the person that asked the question was referring to the hints on the table, but it probably, just as you said, maybe someone else is beside this doctor taking notes with them. Okay, so we also have like a hands up. Tola, would you like to ask a question? Maybe not. Okay, so I think that's all we can take for right now. We have some questions on Slido. If you have a moment, you can have a look. As I mentioned, the last presentation will not be happening. I can give you overview if you would like, but otherwise, we can also conclude today's talk. So what would you prefer? Would you like a very quick overview about the paper and then we conclude, or we just conclude today's presentation session as is, and thank all of our presenters? An overview is fine. Okay. Yeah, let me do that. So as I mentioned, I have a slide from 2021 when I started my working in this domain. So interestingly, my domain is also synthetic data generation. So I thought maybe I could share that. Can you see my screen? I think I'm sharing now.
Yes.
Yes, we can.
What do you see right now? Oh, does it move?
Yes, it's moving.
Yes.
Okay, so the title of the paper that was supposed to be presented is called CITIGAN. I mean, the name of the model is CITIGAN, but it's modeling tabular data using conditional GAN. And the authors were listed in the previous slide. But essentially, I want to quickly give a very quick overview, like why would we want that? So advantages of generating synthetic data usually is because there's a one-to-one relationship between the real record and synthetic record, so people can use this as a replacement of the real data. They assume that then all of the attributes are safe to disclose. Of course, some work have also shown that just generating synthetic data does not make it safe. So you need to introduce some algorithm for privacy protection. But for the sake of simplicity, this is the assumption some of this work are based on, that once you can train a model with a real data and learn from that real data the characteristics of that real data, I'm repeating myself right now, then you can now generate synthetic copies. So nowadays, the methods that are used are usually like deep learning based method. And I quickly just give overview, like there are plenty of works now. In that time, these were the prominent work that have gone through synthetic data generation and for various applications. Previously, there was, like I showed one that did like healthcare, we have finance, we have like other things. But why tabular data, you may ask? A tabular data set is like organizations are increasingly using it. It's very, very widely used. So it makes sense to want to generate synthetic copies for that. And, according to some Kaggle survey, it's also like one of the most popular data modalities. So it gives a nice motivation for why researchers are interested in how we can generate synthetic copies of tabular data sets. And some of the challenges for synthetic data generation, that is what SDG stands for here, is in two folds, and this is exactly what this paper tried to address. The first one is that a lot of when you have a tabular data, in previously you see tabular data as rows and columns, and rows can be like a patient, person, or something. Anything can be a row, but the column usually it's like can be different kind of data type, but for sake of simplicity, usually we deal with numerical columns or categorical columns. So a numerical column in this particular example would be like the temperature column, and the categorical column would be like the outlook column, which is raining, overcast. So when you're trying to train a synthetic data generator, the challenge is how do you represent your numerical column? Because it's like multimodality. Multimodality here just means it has different spikes. If you're familiar with Gaussian distribution, you only have one peak. But here you have multiple Gaussians, if you want to think about it. So it's like mixture of Gaussians. So how do you represent this? Because some of the assumptions that the algorithm that we are considering makes is that the distribution is Gaussian and so on, and this affects the generation process. So this is one of the challenges that this paper tried to tackle by coming up with a better way of representing the continuous column. And they also found out that when you're training the model, you get into a problem with model being like forgetting a mode, like mode collapse problem. So to tackle this particular challenge, they did something called imbalanced categorical column resampling. So it's like training by sampling. And I'll try to give like an overview about the method, see if it makes sense. And you can always go back to reread the paper from that perspective. So I mentioned this, so they have two core contributions. One is this conditional GAN that they proposed, and they also proposed a very nice benchmarking system. By the way, this paper has been cited like so many times. It's whenever anyone starts a new work in synthetic data generation, it always shows up in that paper. So it's a very influential paper for this particular domain. So I mentioned that the continuous column is one of their key targets, and in order to resolve this, they did something called mode specific normalization. So basically, for each of the modes, they just learn another mixture of Gaussian, and then they sample from that. And I'm giving high level now. You would need to sit down with this particular method to get a full understanding of what that happens. But just think about it as they take the raw data, they fit a variational Gaussian model on the raw data. And the nice thing about VGM is that you can sample from some probability distribution, and then they sampled from that probability distribution. So this is now what they fit to their generative model. So this is just like high level. The second innovation I mentioned was that when they were training, they did something like training by sampling. And I listed the problems here. I know it's too much words. I was trying to explain that you shouldn't be doing that, but this was 2021. So I hope I've improved since then. So if they said something like, if the training data are randomly sampled during training, then the rows that fall into the minority category will not be sufficiently represented. So they try to tackle this by when they're training, they're always resampling in a way that all of the minorities gets like the generators sees the minorities during training. And this particular thing is just like they just added like an extra conditioning vector, which maybe it's clearer in this overview. So they would select columns. So D1 and D2 here are columns. Think of it as this numerical column and categorical column that I talked about. So they would select one of the columns, and then they will look at they will randomly select the categories within the column. They turn it into a one-hot encoding vector, and then they fit it into a generator. The generator would also take in some noise because they're using generative adversarial network, which I talk a little bit about in the next slides. And so this is just a process. So we have the generator, and then we have the critic or the discriminator. But it's probably makes more sense to show you here this GAN because it's also very popular. So it's good to know about it. So essentially, how a GAN model works, it's trained in an adversarial way. You have a generator that is trying to generate fake sample. It takes in a noise vector and then generates a very fake data. And then there is the discriminator or the critic that tries to figure out if the generated data is fake or real. So it's the police. So people used to think about it as like you have the thief and the police, or if that makes sense. Anyway, so they play a game all the time. When you're training, they're always playing a game. Generator generates fake data, discriminator try to discriminate. And at some point, while the discriminator is discriminating, they lose some information by telling the generator that this is fake. They kind of like some of the gradients, the generator will use their information to make itself better through the process, the back propagation process. And slowly, generator gets better at generating data. It's like when you're reading all the time, you get better, right? So the discriminator did not know that it's teaching the generator unintentionally, but eventually, they get to a point, the game concludes when the discriminator cannot tell anymore if the generated data is fake or is real. So we'll say we've reached a Nash equilibrium. Then we've been able to generate fake data. So what CityGAN does, build on top of this very good, nice algorithm that was proposed a few years ago, but added some extra, you add on top of existing research. This is how research body grows. And so instead of just the GAN method as it is, they added this conditional vector. So CityGAN is a conditional tabular generative adversarial network. And this on the network architecture. They also propose another one for variational autoencoder, another way to generate data. It's not so important right now. So they propose very two nice architecture, and they have existing code. I really like this. it again, by the way. I my first paper was like on top of it, so yeah, you can imagine. So, but they considered a lot of benchmarking baseline. One of the first family is the Bayesian network, and the second, I know we are over time now, but I'm almost done. The second family is the deep learning based method. And you know, they considered a lot of data sets, adult sensors and so on. Also, they looked at simulated data sets. You know, all story shorts, they outperform usually some of the research. This is how it's heard. So, you know, we do better, but some people don't do better. You know, some of us. But anyway, these are the paper, and then the evaluation framework. Just quickly give you overview. They did something like after they generate the synthetic data, they fit a machine learning model, you know, like your logistic regression or your XGBoost or something. They take the synthetic data, they train the model on the synthetic data, and then they now use like some test sets that was not used at all in the training process to evaluate this model that has been trained on synthetic data. They do the same thing with the real data. They now compare. So if the comparison is similar, you can say that you've generated, I mean, one of the metric is that you can now say, like, claim that you've generated synthetic data that can be used as a replacement for the real data. But of course, in reality, you have to do so many, like, tests on so many different metrics, but this is one metric. And based on that particular metric called machine learning efficacy, they are able to outperform significantly, actually, all of the other methods here. These are the other deep learning based methods. And you can see here that their proposed TVAE and achieved 62% for F1 score. And the identity here is when like you train the training data, like the real data itself. So it would be like the upper bound, the best you can get is this identity. So you can say that it's very, very close in most cases across all these data sets that they considered. So in essence, they provide a flexible and robust model that can learn the distribution of the columns with complicated distributions, as I showed in the motivation slides, and they perform better than these other Bayesian-based method and GAN methods, and you know, it's a nice approach. So that's it about Citigan. Any questions? I mean, I don't think we have time, but you know, you can ask questions for next time. The presenter will give an update, and so you can keep questions in Slido. So, okay. So thank you everyone for today's presentation. I would like to once again thank all of our speakers for the session 2 and session 1 and 2. Once again, thank you so much for taking the time to prepare a slide for this session. And you know, next week we'll be having my very good friend Shewade to give a talk, and he will try to walk you through ways in which you can think about research evaluation. Actually, I should call him Dr. Shewade because he recently got his PhD, like defended his thesis, so he's a doctor now. And we'll also have friends again of mine. They are also all doctors. Interestingly, I'll be the only one that is not doctor because I'm moderating next week's sessions, panel discussion. So I'm very excited that they're coming to talk about research evaluation, and then you know, how to better think about this re-implementing a paper or something like that. And we hope that you can learn from that and take that learning to your week 5 presentation about paper re-implementation. So so that's it, everybody, for today's presentation. Do you have any questions? Okay. It seems not. Okay, that's it then, everyone. See you next time. Have a good rest of your weekend. Thank you for joining us today.